Okay, so let us next see Argand plane and polar representation of complex numbers. And it starts with this, something that we already know. We already know from coordinate geometry that if we use two real lines, one of them as the x-axis and the other as the y-axis, which are perpendicular to each other, and draw them in the two-dimensional plane, then they provide us a way of associating with each point in the plane a pair of real numbers. And you know how that is done. For example, this point in the plane gets associated with this pair of real numbers -1, -1. In a sense, it's like naming each point, giving a name to each point, where the name has two parts. The first part is called the x coordinate of that point and the second part is the y coordinate. It's as if this is the first name and this is the last name of that point. You can think of it in that way. Just like a person has a first name and last name, something like that. Now, so this is something we already know from coordinate geometry. Now let's come to complex numbers. A complex number z is also associated with a pair of real numbers in this way. X and y are real numbers and they are associated with the complex number in this way, where x is the real part of the complex number and y is the imaginary part. So if we combine this with this, then we can associate with each point in the plane a complex number whose real part will be the x coordinate and imaginary part will be the y coordinate. And when we do that, each point in the plane gets a complex number name, or from another point of view, each complex number gets a place in the plane. And in this setup, the plane is called Argand plane or complex plane. The term Argand plane is rarely used. Mostly we call this plane the complex plane. Alright. Okay, so now that we know what complex numbers have to do with the two-dimensional plane, let's see what this association tells us about some other things that we know about complex numbers. For example, let us take a complex number z equal to x plus iy. Now we know that the absolute value or modulus of a complex number is this quantity. Alright, so this we already know about. Now let us look at it from another point of view. Say the complex number is x plus iy, then the point which will represent this complex number geometrically will have its x coordinate x and y coordinate y. Alright. What we do, say that point is this point. We join that point with the origin of our coordinate system by a straight line segment. Alright. Now we know the Cartesian coordinates of the origin. So using the distance formula that we know from coordinate geometry, what will be the length of OP? In other words, what will be the distance of P from the origin? It will be this. So which is nothing but that thing. So we see that in this geometric representation of complex numbers as points in the plane, the absolute value or modulus of a complex number turns out to be equal to the distance of that complex number from the complex number z equal to 0. Okay, so this is the geometric interpretation of modulus. Just like that, there is a geometric interpretation of the complex conjugate as well. Now, before we get rid of this figure, let us see one more thing about this figure. So, you may see that I have drawn some points here. Each point has the two types of names. One type you already know, which comes from coordinate geometry, namely the coordinates of the point. Say this point is -1, -1. And the other type, of course, we have seen just now is that the associated complex number. -1 minus I will be this point. -3 minus 4I will be this point. 2 plus 2I will be this point because its coordinates are 2, 2. Like that, the points on the x-axis also have actually two coordinates. The y-coordinate is consistently 0. The x-coordinate, however, will change. For example, this point, which is at unit distance from the origin and on the x-axis to its right, has the coordinates 1, 0. As such, it gets associated with the complex number 1 plus 0i. But this 1 plus 0i really is a real number, right? So just like that, the complex numbers that get their places on the x-axis are actually real numbers. And that is why this axis is called the real axis. In the context of this association between complex numbers and points in the plane, this axis is called the real axis because the real numbers make this axis. Similarly, if you think of this complex number I, which is 0 plus 1i, it comes from the point whose coordinates are 0, 1, and that point is here. On the y-axis, above the x-axis, 1 unit above the x-axis. That complex number, however, is a purely imaginary number because its real part is 0. Similarly, all other purely imaginary numbers lie precisely on the y-axis, and that is why this axis in this context is called the imaginary axis. Let us next see what geometric interpretation we can give for the complex conjugate of a complex number. Say our complex number is 2 plus 2i. Then what is its complex conjugate? 2 minus 2i. To form the complex conjugate, we change the sign of the imaginary part. Here the imaginary part is 2, we make that minus 2. So that way we get the complex conjugate 2 minus 2i. Now, what places do they take in the complex plane? Let's see the relationship between these 2 points geometrically, the geometrical relation. If you draw the 2 points, you see that they lie along this vertical line, x equal to 2. And this is the complex conjugate and this is the original complex number. And their distances from the x-axis are the same, which means that this complex conjugate 2 minus 2y is the mirror image of this complex number 2 plus 2y on the x-axis, as if the x-axis is a mirror and like this. It's a plane mirror and 2 plus 2y is standing here and it's looking in the mirror and seeing itself there. Okay, this is where its reflection lies. So the complex conjugate is the reflection of the original complex number on the x-axis. Now if you change the perspective, say your original complex number is 2 minus 2y, which is looking into the x-axis, which is again a plane mirror but now facing this complex number. Then what is its complex conjugate? Again we have to change the sign of the imaginary part, that gives us 2 plus 2y. So the reflection of 2 minus 2y in this mirror is lying here. That is why these two complex numbers are mirror images of each other on the x-axis. That's the geometric interpretation of a complex number and its complex conjugate. They are mirror images of each other. And you can clearly see that the same thing will happen with any complex number, no matter where it is located. Say you have some arbitrary complex number here, then its complex conjugate will be its mirror image. And the numbers that lie on the real axis, that is the real numbers, are somewhat special in this respect because they will be their own mirror image, which we can see geometrically. Is it really the case? Let's see. So a real number is a complex number like this. So if you take its complex conjugate, you change the sign of the imaginary part because the imaginary part is 0, essentially nothing changes. You get x minus I0, but that is still x. So that's the geometric interpretation of complex conjugate. Next, let us see polar representation of a complex numbers. And for that, we need to first of all look at what polar coordinates are. Although most of us already know what polar coordinates are and what the polar coordinate system is, but let's just quickly see what it is. So here, instead of x and y axis, we have only one axis, and that too, it's not a straight line. I mean, it is a straight line, but it's a part of a line, half of a line. It's a ray which is bounded on one side. At this point, it starts from there and then goes in one direction indefinitely. And this line is called the initial line. And the point from where it starts is called the pole. Now say a point is given in the two-dimensional plane in which this line also lies. Now what are the polar coordinates of P? To know that, you first join P and the pole by a straight line segment. And that straight line segment will then have a length. Say that length is r. And there is another number that can be associated with P, because we are talking about the coordinates of P in the two-dimensional plane. So no matter what coordinate system you use, polar or Cartesian or anything else, you are going to need two numbers because it is two-dimensional. So that other number is related to the angle that this line segment OP makes with the initial line. The problem is which angle. You may say that this angle, theta. Okay, fine, that is one angle that OP makes with the initial line, but there are other angles also. For example, you can think of this angle as well. Why should we not choose that? That is also an angle that OP makes with the initial line. And in fact, these are not the only angles, because We have already gone through trigonometry and we know that for us angles are rotational angles. So if you have one such angle theta, you can then add any integer multiple of 2 pi to that theta and you can still have that same position. I mean, if you are thinking of theta as the rotational angle where the rotation starts from the initial line, then if you rotate this much, you get the position OP. However, if you rotate by this angle, theta plus 2 pi, what type of rotation will that be? 2 pi means one complete rotation and an additional theta. So you again come back to that position. So in that sense, this is also an angle that OP makes with the initial line, and that way you can clearly see that there are infinitely many angles. You can consider this, you can consider theta plus 4 pi, many angles you can consider, and that is why that other number theta besides r that you are going to associate with P is not unique actually. Not unique. In fact, there are infinitely many choices for that angle. Regardless of this lack of uniqueness, any such theta can be chosen and you can consider this ordered pair of r and theta. These are polar coordinates of P, but we cannot say the polar coordinates because theta part is not unique. Actually, you can choose r to be negative also, but because we are not going to need such complexities from the polar coordinate system in our application here, so we consider r to be positive only. Okay, so this is one problem that you have with theta. R, however, is going to be just one thing, which is just the distance of P from the pole. Alright. Now we are going to use this fact to give a different representation to complex numbers than the one which we have, that is z equal to x plus iy. The way we have associated complex numbers with points in the plane made x the x coordinate and y the y coordinate of that point. Okay, so now instead of these Cartesian coordinates, we want to use polar coordinates of that point to which z is associated in the plane. How can we do this? Let's see. So this is the setup. We have the complex plane. So the complex plane always comes with the real axis and imaginary axis. Those things are always there. And say our point is P with x coordinate x and y coordinate y, and it is associated with the complex number z equal to x plus iy or x plus yi. So what we do, how can we introduce polar coordinates here? Well, for that, first of all, we are going to need an initial line and a pole. We make the positive x-axis, or rather the non-negative x-axis, because the point, this origin is going to be included as our initial line. And this is going to be our pole, or in fact, this origin of the Cartesian coordinate system will be our pole. Alright. Then what will be that r? R in this case, of course, is going to be just the modulus of our complex number. We have already seen this. Theta, however, is one of those angles. Okay, and here also we allow theta to have any value. The only thing is that after you complete the rotation, whatever value theta tells you, by which you have to go through that rotation, which starts at the initial line but it must end here. The terminal line of that rotation should be along OP. Alright. Then the polar coordinates of your P are r comma theta. Okay, fine. But now what is the relationship between the Cartesian coordinates and polar coordinates? The relationships are these: x equal to r cos theta, y equal to r sin theta. But the question is why? How? And the answer is this. You see, say you consider this point. So what we have done here is that we have drawn the unit circle centered at the origin and having radius 1, of course, because it's the unit circle. If the distance between O and P is greater than 1, then the unit circle is going to intersect OP. But that's not necessary. P may be closer to O than the distance 1. In that case, OP will lie here. But in that case, you can extend the line by drawing it more. Then that extended line will be intersected by the circle at some point. Say that point is P prime. Okay. Now, so we want to know how these relations arise, right? You consider this point in the Cartesian plane. Are you able to divide by r? Yes, you are able to divide by r, provided r is not equal to 0. So, to be able to consider this point, we need the condition that r is not equal to 0, which will happen if P does not coincide with O. That means we are considering any point in the plane except the origin or except the pole. Fine, then we can consider this. However, what type of relation do these coordinates satisfy? If you remember what r is this, right? So what is r square? I can show it here itself. R square is x square plus y square. Now if I divide on both sides by r square, then I am going to get 1 equal to x divided by r square plus y divided by r square. So we see that the point x over r comma y over r lies on that unit circle. Actually that point is nothing but this P prime. Because it satisfies the equation of the unit circle, that is why. However, In this situation, what do you know from the definitions of trigonometric functions? That the x coordinate of the point is defined to be cos theta and the y coordinate is defined to be sin theta. This is the x coordinate. So this should be cos theta because this is what cos theta means, and this is the y coordinate, so it should be sin theta. And this relation gives you this and this one gives you this. So that's how the relationship between Cartesian and polar coordinates arise. Okay, fine. So we have understood this. Now what are we going to do with this information? We are now going to use this information back to the original representation of the complex number using x and y. Now we can use r and theta instead to express that complex number y. So in its place, now you have r cos theta plus I r sin theta. If you take r common out, you get cos theta plus I sin theta. This representation of z in terms of r and theta is called the polar representation of this complex number. And do not forget this condition, okay? Because we needed this condition to establish this relation, this means that every complex number has a polar representation except the complex numbers z equal to 0. Okay, so that restriction is there. So that's the polar representation, nothing else. Now there are some things associated with the polar representation of a complex number, one of which we already know, the other one we are going to see now. The polar representation of a complex number are of course r and theta. R is just this, which you know as the modulus or absolute value of the complex number z. Theta, however, has a name also. It's called an argument of z. An argument we say because theta is not unique. You may put one value of theta, someone else may put another value of theta. Cos theta and sin theta, however, are going to be same. Okay, so that thing is there. The different choices of theta are not going to change what z is. The thetas may be different, but ultimately the complex number will be just that same complex number. But anyway, for a single complex number, you actually have infinitely many values of theta. So all those thetas are called arguments of the complex number. And any such argument is denoted by this notation, Rz. Now in order to have uniqueness, you can either put this restriction on theta, you can require theta to be non-negative and less than 2 pi, or if you put this restriction, then you will get only one value of argument. Okay, so that way you can get uniqueness. Another restriction is this. That your theta is required to be greater than minus pi but less than or equal to pi. If this restriction is put on your argument, then also you get a unique argument, different from this one. And this unique argument has a name. It's called the, now you can say the principal argument of z. Just like any arbitrary argument is written like this arg z, the principal argument is denoted by capital Rz. What those restrictions on theta mean geometrically, and what do those restrictions have to do with the location where the complex number is in the complex plane. Say the complex number lies here, Z. Then you can join Z and the origin or the complex number 0 and say our restriction is this type of restriction. Then for this type of location, if the complex number lies in the first quadrant, this is your theta. Note that I am showing an arrow also because my rotational angles need to be non-negative. They cannot be negative, so I need to always have anti-clockwise rotation, not clockwise rotation. If the complex number lies in the second quadrant, my theta is going to be this rotation, still anti-clockwise rotation. If it lies in the third quadrant, say here, then this will be theta. If it lies in the fourth quadrant, then this will be theta. Okay. And we are not going to need any further rotation than this because of this restriction. For example, for this complex number, you can actually think of another argument which exceeds this restriction, which goes beyond this restriction. And that rotation is this and then this. That is also an argument of Z, but that is not this type of argument. Alright. Principal arguments of complex numbers look geometrically. So if my complex number lies in the first quadrant, so for principal arguments, the restrictions are these, right? So if my complex number lies in the first quadrant, then of course I first join it with the origin, with the complex number 0. Then the principal argument will be this. Okay, so it's satisfying these inequalities. If it lies in the second quadrant, then this is the principal argument. However, if my complex number lies in the third quadrant, say here, then I can no longer consider anti-clockwise rotation. Yeah, I messed this up a little, but you understand the figure, it's supposed to go there. I can no longer have this type of rotation because that exceeds pi, and that is why I am forced to consider clockwise rotation, which however is allowed because theta can be negative here. Okay, so this becomes my argument. Similarly, if the complex number lies in the fourth quadrant, then this clockwise rotation becomes the argument. Alright. Then we are going to complete this video. In this example, we have the complex number z equal to 1 plus root 3i, and we have to turn it into the polar form. Keep in mind that this requires us to know two things. One is that r and the other one is theta, and theta can be any theta. In the polar form, there is no restriction on theta. The polar form specifically does not require you to find the principal arguments. Any argument will do. So let's see how we can do this. Here, you can start like this actually. Instead of writing here, you can start like this. Let z equal to r times cos theta plus I sin theta b. Actually, strictly speaking, we should not say the polar form because that theta can change. But anyway, I am just writing the polar form. Polar form of z. Okay, but we know what z is. Then 1 equals r cos theta and square root of 3 equals r sin theta. Now you can directly write the fact that r is the absolute value of z, or if you want you can find r from these two equations as well by squaring and adding them, because then this side will become 1 square plus root 3 square and that side becomes this, which will be r square. So this will become 4. Now keeping in mind that r is positive, you get r equal to 2. It looks a little weird because you have r on that side. You can start the equation like this. You write this on this side and you just interchange the things. But anyway, r is 2. Hence, 2 cos theta equals 1 and 2 sin theta equals root 3, or cos theta equals sin theta equals square root of 3 over 2. Thus, you can clearly see that the value, this works and it satisfies both the equations. So, the polar form is z equal to 2 times cos pi over 3 plus I sin pi over 3. Now do not again write 1 over 2 here, okay, because it's from there only you are coming to this. Again, don't go back. This is the polar form. Complex number into the polar form. So the complex number is given in a little complicated way. So let us first express this in the form a plus ib, then only we can proceed. We have, let's give it a name also. Let z be the complex number, 1 plus root 3i. I hope I have taken this down correctly. Yes, okay. So we multiply and divide by the complex conjugate of the denominator So that will make the denominator what? 1 plus 3 actually, which is 4, and that way we get, so you will have 4 here. Let me actually write 4. After cancellation with this minus 16 and after multiplication, we get minus 4 plus I times 4 root 3. So this is our complex number. The polar form B z equal to r times cos theta plus I sin theta. Thus, so what are the equations we are getting? R cos theta equal to minus 4 and r sin theta equal to 4 root 3. So this time let me just directly write this. There is a square root, we should not forget that, plus 4 root 3 square and 16, and then doing all the calculations. We can smartly take the 4 square outside the square root, and that way we will get 4 outside, and inside we will have 1 here and 3 here. So 4 times 2 will be 8. So this is our R. So 8 cos theta equals minus 4 and 8 sin theta equals 4 root 3, or if you simplify a bit you get this, and sin theta is square root of 3 divided by 2. This tells you that the complex number lies in the second quadrant because cos theta is negative and sin theta is positive. Recall what we did over there. We first did not think of the minus sign, and what value of theta gives us cos theta equal to 1 over 2 pi over 3. But we need to be in the second quadrant, so we try pi minus pi over 3. But we don't really know whether this will work. Let's calculate this. So if you apply the cos A minus B formula, you get cos pi over 3 plus sin pi over 3. This is rough work, okay. Sin pi is 0, cos pi is minus 1, and cos pi over 3 is 1 over 2. So yes, you are really getting minus 1 over 2. What will happen if I calculate the sin? You may already know that this is sin pi over 3, but still let me just apply the formula. Minus cos pi sin pi over 3. This part is 0, so the first term vanishes. Cos pi is minus 1. That minus and this minus give us plus sin pi over 3, which is root 3 divided by 2. So yes, it works. This angle works. That is 2 pi over 3. Hence, the polar form is z equal to 8 times cos 2 pi over 3 plus I sine 2 pi over 3, and that's the example. This is how you can find arguments of a complex number. And if you are asked to find the principal argument of a complex number, you will then have to find a value of theta that satisfies that condition that it lies between minus pi and pi in that specific way. It is greater than minus pi but less than or equal to pi. But anyway, that will be all for tonight, and tomorrow also of course we have our upload. So see you tomorrow with whatever there is. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.